In this example, we want to evaluate the integral below, so the integral over r of y sine of xy, integrating with respect to area, where r is the region bounded by the curves y equals 1 over x, y equals 4 over x, and y equals 4 and y equals 1. So if we go ahead and sketch that region R, what we're going to see, so we've got y equals 4 up here, y equals 1 down here, and then y equals 1 over x. We're only going to need the first quadrant portion of it because the other portion is in the third quadrant, which doesn't intersect those horizontal lines. So this is y equals 1 over x, and then y equals 4 over x. We've got this region here. So again, what we might notice is in terms of rectangular coordinates, this region is not particularly super nice. We'd have to find a lot of intersection points and split it up into multiple pieces. However, we have different curves that have similar structures to them. So doing a change of variables might be really nice. So again, we might want to try and rearrange things so that we have some formulas that are equaling a constant, so kind of moving everything over. So we might rearrange this to say be the equation xy equals 4 and xy equals 1, which is the same equation. We just have a slightly different arrangement of it. What we then could take a look at is trying to find some substitution. So then really what we have is we were in a way going from, say, this inner curve to this outer curve, which both are in terms of xy. So we might do something like let u be xy, because then what we're going to have is that u just goes from 1 to 4, right? We go from xy equals 1 to xy equals 4. And then my other variable, if we're then trying to create kind of a rectangular region, we could go from this bottom curve to this top curve. Now both of those are just defined by y equals. We could just simply let v equal y. So then v goes from also 1 to 4. So when we draw our region S in the UV plane, both of them just go from 1 to 4. So we just end up with a rectangular region rather than this complicated region of R. So my bounds are going to become much more simple. Now, what I want to try and take a look at next, remember, is we need to figure out, though, how do we substitute things in to our function, and we still need to find our Jacobian. So we've got our functions for u and v. We need to now find those in terms of x and y. So if u is xy and v is y, well then even right away here I could see that we could sub that v in to this formula. So then we would have u is really xv, which then I could solve that for x to have that x is going to be u divided by v. So then we have x is u divided by v, and well, y was just v. So we can leave y equals v as an equation. So we've got x is u over v and y is v. Notice this is going to work perfectly fine when we try and sub those into our integral. It's actually going to work really nice, where we're going to have a v on the outside, and then inside of the sign we're just going to have u, which will actually turn out quite nice. But let's go ahead for now and find our Jacobian. Remember, never forget the Jacobian. Don't forget Jacobian. We need to find the Jacobian for xy in terms of uv. So we'll set that up in our determinant form. So we need the partial of x with respect to u first. So the partial of x with respect to u, partial of x with respect to v is what will come next, partial of y with respect to u, and then the partial of y with respect to v. When we take the derivative of x with respect to u, notice it's really just u times the constant 1 over v, so we'll keep 1 over v. When I take the partial of x with respect to v, it's really u times v to the negative 1. So we bring that negative down, and then the power on u becomes a negative 2 because it decreases. So that's really divided by v squared. And then for y, the partial of y with respect to u, well, v is constant with respect to u, so that's just going to be a derivative of 0. And then the derivative with respect to v is 1. So then we compute this by multiplying on the main diagonal. So we'll have 1 over v times 1, and then we do minus the opposite diagonal. So we'll really have minus then negative u over v squared, but it's just times 0. We'll really just have minus is 0. So all in all, I get 1 over v. When we do then put everything in our integral, remember we had the integral of r of, I think it was y sine of xy dA. Let's just double check that, make sure I didn't copy that wrong. Yep. We're switching this now to our uv integral. So we found our bounds here. Both the bounds of u and v go from 1 to 4. So this is going to equal the integral from 1 to 4, the integral from 1 to 4. We've got to sub things in. Y equals v. So we'll have v. And then we'll have sine of xy, which we could either look at as x is uv times v, which simplifies to u, or we can remember that u was defined as being xy. So this is just going to be sine of u, and then this is du. Oops, what did I forget? I forgot the Jacobian. Never forget the Jacobian. Because remember now, we need to multiply by the absolute value of our Jacobian, which is 1 over v. And then this will be, we can do du dv or dv du, but let's do du dv. Do notice then, we do know that v, we're only looking at v on 1 to 4, so the absolute value of 1 over v is really just going to be 1 over v, right? It'll stay positive because it's all positive values in there. So what happens then if I have v times 1 over v? Well, they just cancel out. So we're left with the integral 1 to 4, 1 to 4. We'll have 1 over v times v just leaves me with the integral of sine u, and then this will be du dv. So then now the integral of sine of u du is negative cosine u. This is going to be from 1 to 4. And then we're still doing that integral from 1 to 4 dv. So this is the integral from 1 to 4. We're going to have negative cosine 4 minus a negative, so plus cosine of 1 dv. And we'll just leave those in terms of cosine because they're not particularly simple reference values. So then let me just rearrange it so that it's positive first. So we'll have cosine of 1 minus cosine of 4. So then that'll be all times v, where then v is evaluated from 1 to 4. So we're going to have 4 times that cosine, 1 minus cosine 4. minus 1 times that cosine 1 minus cosine 4. So then we're left with 3 times cosine of 1 minus cosine of 4 would be the evaluation of that integral. So switching those bounds really made this a pretty nice integral to solve. We just had some simple constant bounds. Whereas if we had done it originally how it was listed and kept it in rectangular coordinates, both actually the bounds would have been more complicated. We would have had to split up our integral, or likely we would have switched it and done a left-right integral. So we would have done like a dx dy integral. But then our integration actually would have been slightly more complicated as well for this example.